At the smallest scales our equations can reach, energy stops behaving the way we expect, not because the universe becomes chaotic, but because our descriptions quietly fall apart. There is a boundary where space, time, and energy blur together so completely that even our most trusted theories no longer agree. This boundary is not loud or violent, it is subtle, measured, almost impossibly small. If this quiet journey brings you even a moment of peace or wonder, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these calm explorations alive, and I hold that support with sincere thanks. Now we turn the page together. Part 1 waits just ahead. Part 1. The Scale. Where physics begins to whisper. At a distance smaller than anything we can picture, energy and geometry become inseparable. If you could keep zooming in, past atoms, past nuclei, past quarks, you would eventually reach a scale where adding energy no longer reveals detail, but instead reshapes space itself. This is where the idea of Planck energy quietly emerges, not as a discovered object, but as a limit written into the structure of reality. If you imagine shrinking yourself down, not physically but conceptually, the journey begins gently. First, you pass the familiar world of molecules, where chemistry governs how matter binds and reacts. A little deeper, atoms dissolve into a tiny nucleus wrapped in a soft cloud of probability. Go further still, and even the nucleus gives way, revealing protons and neutrons, then quarks, flickering in and out of existence under the rules of quantum mechanics. At each step, the universe seems willing to cooperate, offering structure in exchange for energy. But something subtle changes as you continue. Each new layer requires more energy to see. This is not a limitation of human tools, but a fundamental rule of nature. To resolve smaller distances, you must use probes with shorter wavelengths, and shorter wavelengths always mean higher energy. It is a quiet trade the universe insists upon. Detail is never free. It is purchased with energy, paid in exact proportions. For most of scientific history, this trade felt generous. Each increase in energy revealed something new. Atoms, then nuclei, then quarks. The pattern suggested that reality might be endlessly divisible, a nesting of smaller truths waiting patiently beneath the surface. For a while, physics followed this expectation with confidence. The deeper we looked, the more the universe revealed, as though depth itself were infinite. Yet as you approach the smallest meaningful scales, the bargain begins to shift. Energy stops behaving like a passive tool and starts acting like a force with consequences. According to Einstein's relativity, energy and mass are interchangeable, and both tell spacetime how to curve. At everyday scales, this curvature is imperceptible, but when energy is compressed into an extremely tiny region, its gravitational influence can no longer be ignored. This is the moment where physics begins to whisper instead of speak clearly. As you concentrate more energy into a smaller space, space-time responds. It bends. Distances stretch and contract. Time itself slows relative to its surroundings. At first, these effects are tiny mathematical curiosities measured only by precise instruments. But the trend is unmistakable. More energy does not merely illuminate smaller structures, it actively reshapes the stage on which those structures exist. There comes a point where this reshaping overwhelms the act of observation. Instead of revealing finer detail, the energy you add begins to collapse the region you are trying to examine. Space curves inward. Paths of light bend back on themselves. What you hoped would be a clearer view becomes a horizon beyond which no information escapes. This threshold is not arbitrary. It is defined by a specific scale where quantum mechanics and gravity become equally important. The energy associated with that scale is what physicists call Planck energy. It is not something we have measured in a laboratory, nor something we expect to encounter directly. It exists as a boundary condition, a line drawn by the mathematics of the universe itself. Planck energy emerges from a simple but profound act of combination. Take the fundamental constants that govern nature, the speed of light, which limits how fast information can travel, Planck's constant, which sets the scale of quantum uncertainty, and Newton's gravitational constant, which determines the strength of gravity. When these three are woven together, they produce natural units: Planck length, Planck time, and Planck energy. These units do not depend on human conventions. They belong to the universe, whether we measure them or not. What makes Planck energy so striking is its magnitude. It is extraordinarily large by any standard, far beyond the energies reached in even our most powerful particle accelerators. Yet it corresponds to an extraordinarily small length. This pairing is the heart of the mystery. Immense energy compressed into an almost inconceivably tiny region is exactly what gravity reacts to most strongly. At this scale, the familiar separation between objects and the space they occupy dissolves. Space is no longer a passive container. It becomes dynamic, reactive, uncertain. The smooth geometry described by general relativity begins to fray, while the probabilistic rules of quantum mechanics strain under the influence of intense curvature. Neither theory fully applies on its own, and together they speak in contradictions. This is why Planck energy is often described not as a physical thing, but as a warning. It marks the point where our current descriptions stop agreeing with each other. Beyond it, words like distance, duration, and even energy lose their usual meaning. The universe does not disappear there, but our language for describing it does. If you pause here for a moment, there is something deeply calming in this realization. The universe is not obligated to be endlessly accessible. It does not promise infinite layers of clarity. Instead, it offers structure up to a point and then asks for humility. There are depths where curiosity must slow down, where questions outpace answers, and where silence replaces precision. Importantly, this boundary is not merely technological. Even with perfect instruments, the physics itself resists deeper probing. Any attempt to look closer by adding energy only strengthens gravity's grip, erasing the very details you seek. It is as though reality protects its foundations, not through force, but through balance. This balance hints at something profound. Perhaps space-time itself is not infinitely divisible. Perhaps there is a smallest meaningful scale beneath which the concept of where loses coherence. In this view, Planck energy is not a barrier imposed from outside, but a reflection of how reality is built. A graininess woven into existence, subtle and unobservable from afar, yet decisive at the deepest level. Physicists sometimes describe this realm using metaphors like foam or flicker. These are not poetic exaggerations, but attempts to gesture toward behavior that resists direct description. At such scales, space-time may fluctuate violently, forming and dissolving structures faster than they can be defined. Cause and effect blur. Before and after lose their clean separation. And yet, from this uncertainty, everything familiar eventually emerges. Galaxies form, stars ignite, atoms settle into stable patterns. The calm, continuous world you experience right now may be an average, a smoothing over of deeper turbulence that never truly disappears. Planck energy, then, is not distant from your life. It is the quiet foundation beneath it. As you breathe, your body exists comfortably far from this boundary. The energies involved in everyday matter are unimaginably smaller. Gravity is gentle. Quantum uncertainty averages out. The universe feels solid, reliable, and slow. That contrast is part of what makes the Planck scale so humbling. It reminds us that stability is not guaranteed everywhere. It is a local gift. Scientists continue to search for a deeper theory that can speak calmly at this scale, a framework where quantum mechanics and gravity no longer argue but cooperate. Whether that theory will reveal new dimensions, discrete space-time, or something entirely unexpected remains unknown. For now, Planck energy stands as a signpost, marking the edge of understanding rather than its conclusion. And as this quiet journey continues, another question begins to form. If energy and size are so intimately linked at the smallest scales, why does looking closer always demand more energy in the first place? What is it about nature that ties resolution to intensity so tightly? That is the next whisper waiting to be heard. Part 2. Why energy and size are secretly linked to see something. Smaller, physics demands higher energy. This rule has guided every microscope and particle accelerator ever built. But as energy increases, it begins to curve spacetime, just as mass does. Slowly, almost imperceptibly, the act of observation becomes an act of distortion. At extreme scales, energy no longer illuminates, it collapses. If you trace this rule back to its simplest form, it begins with waves. Light, sound, even matter itself behave as waves under the right conditions, and every wave carries a defining property, its wavelength. Long wavelengths spread gently, revealing only broad shapes. Short wavelengths oscillate rapidly, capable of resolving fine detail. This relationship is calm, mathematical, and unyielding. To see smaller structures, you must use waves with shorter wavelengths. Shorter wavelengths, however, always come with higher energy. This is not a technological inconvenience, but a fundamental law of nature described by quantum mechanics. A photon of visible light carries far less energy than an X-ray photon, and an X-ray carries far less than a gamma ray. Each step toward smaller wavelength is a step upward in energy. Resolution and energy are bound together, quietly and permanently. This is why early microscopes reached their limits so quickly. Visible light simply could not resolve objects smaller than its own wavelength. To see atoms, scientists turned to electrons, which also behave like waves when accelerated. Faster electrons mean shorter wavelengths, and again, faster means more energy. The pattern repeats without exception. At human scales, this trade feels benign. Increasing energy improves clarity without consequence. An electron microscope does not noticeably bend space. A medical X-ray does not curve time. Energy seems like a passive currency we can spend freely to buy detail. But this comfort exists only because we operate so far below the universe's deeper thresholds. As energy rises, something subtle begins to change. Energy is not just a tool for probing matter, it is a source of gravity. Einstein showed that mass and energy are equivalent, and both contribute to the curvature of spacetime. At everyday energies, this curvature is vanishingly small, but gravity never truly disappears, it only waits. Imagine concentrating energy into an increasingly tiny region, the way particle accelerators do when smashing particles together. Each collision packs tremendous energy into a minuscule volume for an instant. For now, gravity remains negligible. The space-time distortion is too small to matter, but the equations tell us that this cannot continue forever. As you push toward smaller and smaller scales, the energy required rises faster than intuition expects. The relationship is steep, almost unforgiving. Eventually, the energy density becomes so high that gravity can no longer be ignored. The spacetime in that region begins to curve measurably, even violently. Paths of particles bend. Time slows locally. The geometry you assumed as a backdrop starts to participate in the experiment. This is where the act of observation transforms. You are no longer shining a light into darkness, you are reshaping the darkness itself. At extreme energies, the very notion of looking breaks down. The probe you send in, whether a photon or a particle, carries so much energy that it alters the region it enters. It is like trying to study the surface of a calm pond by dropping a stone into it. The ripples you create overwhelm the detail you hope to see. At the smallest conceivable scales, this disturbance becomes total. According to general relativity, enough energy confined to a small enough space will create a black hole. Not a dramatic star-devouring monster, but a microscopic horizon where space-time folds inward. Nothing escapes, not light, not information. The region you tried to observe vanishes behind its own gravity. This is why energy and size are not merely linked, but locked together. The universe enforces this relationship as a kind of balance. You may trade energy for resolution, but only up to a point. Beyond that, the trade reverses. More energy gives you less access, not more. There is something deeply elegant about this limit. It suggests that nature is not infinitely transparent. Reality does not allow itself to be dissected without consequence. The smallest scales are protected not by mystery alone, but by the same laws that govern stars and galaxies. Gravity, usually the weakest of forces, becomes the final gatekeeper. This also explains why Planck energy plays such a central role. It marks the scale where the energy required to probe a region is sufficient to collapse that region gravitationally. At this point, quantum mechanics and gravity confront each other directly. One demands higher energy for better resolution. The other responds by closing the window entirely. From a distance, this might seem frustrating, even limiting. But from another perspective, it is stabilizing. If energy and size were not linked this way, the universe might be fundamentally unstable. Infinite detail could imply infinite energy, infinite curvature, infinite chaos. The fact that such infinities are avoided hints at an underlying consistency we have not yet fully grasped. As you rest here, listening, it's worth noticing how far removed your everyday experience is from this struggle. The light in the room does not warp the walls. The sound of your breath does not bend time. The energies involved in life are gentle, balanced, safely distant from these extremes. That separation is what allows complexity, memory, and calm to exist at all. Yet the rule remains universal. It applies everywhere, always. Even in the earliest moments of the universe, when everything was compressed into a tiny, hot state, energy and size were inseparable. As the universe expanded and cooled, energy densities dropped, allowing space-time to smooth out. Structure became possible precisely because energy relaxed its grip. This connection between energy and scale also shapes the future of physics. Any theory that hopes to describe reality at its deepest level must respect this balance. It must explain why energy reveals structure at some scales and hides it at others. Why curiosity encounters clarity first, then resistance, then silence. Some theories propose that space-time itself is quantized, made of discrete units that cannot be subdivided. Others suggest extra dimensions curled so tightly that only immense energies could ever reveal them. Still others imagine entirely new principles waiting beyond the Planck scale. What they share is an acceptance of this central truth. Seeing smaller is never neutral. It always comes at a cost. There's a quiet philosophical weight here. Knowledge is not just about asking questions, but about how we ask them. In physics, the question, "What is smaller?" cannot be separated from how hard are you willing to push. At the deepest levels, pushing too hard erases the answer, so energy and size remain bound together, not by accident, but by design. A design not planned, but emergent. A rule that keeps the universe both knowable and protected, open and closed at once. And as this understanding settles, another question gently takes its place. If energy curves space-time and limits our vision, what happens when gravity and quantum uncertainty meet on equal footing? What kind of world exists where neither can dominate? That is the quiet threshold waiting in the next part of our journey. Part 3. The birth of Planck units. Planck energy does not come from experiment, but from mathematics. By combining three constants, gravity, quantum mechanics, and relativity, physicists uncovered a natural system of limits. Planck length, Planck time, Planck energy. Together, they describe a regime where our familiar concepts stop working, not because they are wrong, but because they are incomplete. To understand how these units were born, it helps to step back into a quieter moment in scientific history, before particle accelerators and space telescopes, when much of physics was still guided by pencil, paper, and careful thought. At the turn of the 20th century, physicists were struggling with a growing tension. The laws that governed the very large and the laws that governed the very small did not speak the same language. Gravity ruled planets and stars. Quantum mechanics ruled atoms and light. Each worked beautifully in its own domain. Together, they refused to cooperate. In 1899, a German physicist named Max Planck noticed something subtle. Certain constants kept appearing again and again in the equations that described nature. Not arbitrary numbers chosen by humans, but fundamental values woven into reality itself. There was the speed of light, setting the ultimate limit on motion and information. There was his own constant, Planck's constant, defining the smallest possible action in the quantum world. And there was Newton's gravitational constant governing the strength of gravity. Planck asked a gentle but radical question. What if we built units of measurement using only these constants, with no reference to human-made scales like meters, seconds, or kilograms? What if the universe already had its own natural units, waiting quietly beneath our conventions? When he carried out this combination, the result was astonishing. Out came a length unimaginably small, a time unimaginably brief, and an energy unimaginably large. These were not guesses. They fell directly out of the mathematics, as cleanly as a chord resolving in music. The Planck length emerged as the scale at which spacetime itself might lose meaning as a smooth continuum. The Planck time appeared as the smallest interval over which cause and effect could still be defined, and Planck energy stood as the energy scale where gravity and quantum effects become equally strong. What is striking is how indifferent these units are to us. They do not care about human perception, biology, or technology. They are not tuned for comfort or intuition. They simply exist, implied by the constants that govern everything else. In this sense, Planck units feel less like inventions and more like discoveries of something the universe had already decided. At first, these units seemed like curiosities. There was no experiment that could reach them, no immediate application. But as physics progressed, their significance deepened. Again and again, whenever equations were pushed to their limits, divergences and infinities appeared precisely at these scales. It was as if the mathematics itself was pointing to a boundary, a place where new rules must take over. The Planck length, for example, is not merely small. It is so small that if an atom were expanded to the size of the observable universe, the Planck length would still be smaller than a grain of sand in that vast space. At this scale, the idea of a point in space becomes questionable. The notion of a precise location dissolves into uncertainty. Planck time is even more unsettling. It represents the time it takes light to travel one Planck length, not a tick of a clock, but a conceptual minimum. Below this interval, the sequence of events may lose meaning. Before and after blur. Time itself becomes difficult to define. Planck energy, sitting alongside these, completes the triad. It is the energy associated with compressing matter or radiation into a region the size of a Planck length. At this energy, the gravitational effect of that energy becomes so intense that space-time curvature can no longer be treated as a background. It becomes part of the system. Together, these units define a regime where our trusted tools fail, not due to error, but due to overextension. Classical concepts like position, duration, and trajectory rely on space-time being smooth and separable. Quantum mechanics relies on probabilities defined over that space-time. General relativity relies on space-time being a continuous geometric object. At the Planck scale, these assumptions collide. There is something deeply reassuring in this. The failure is not chaotic, it is consistent. Every path leads to the same boundary. Whether you approach from quantum theory or from gravity, you arrive at the same conclusion. Something fundamental changes here. As you sit quietly, it's worth noticing how these units reframe perspective. The second you experience feels solid and continuous, yet it is composed of intervals trillions upon trillions of times larger than the Planck time. The space around you feels smooth and reliable, yet it may be built upon a structure so fine that smoothness is only an approximation. Planck units remind us that much of what feels absolute is emergent. Length, time, and energy behave the way they do because we live far from the extremes. Our reality is a middle ground where averages dominate and fluctuations cancel out. At the Planck scale, averages no longer apply. Physicists sometimes describe this as the universe having a resolution limit, not in the sense of a screen or a simulation, but in the sense that there is a smallest meaningful distinction. Beyond that, questions about where and when lose their footing. The universe does not provide finer answers because finer answers may not exist. This does not mean the Planck scale is empty. On the contrary, many suspect it is intensely active. Quantum fluctuations may tear space-time into fleeting geometries. Tiny black holes may form and evaporate. Dimensions may compactify and unfold. But whatever happens, there does not map cleanly onto our everyday language. Importantly, Planck units are not barriers we will someday break through with better technology. They are not speed limits waiting for faster engines. They are indicators of a conceptual transition. To go further, physics must change its questions, not just its tools. This is why so much effort is devoted to theories like quantum gravity, string theory, and loop quantum gravity. Each is an attempt to speak coherently at the Planck scale, to build a language that remains calm where current theories stutter. None has yet been confirmed, but all take Planck units as their starting point, not as obstacles, but as guideposts. There is humility in this approach. Instead of forcing nature to fit existing frameworks, physicists allow the frameworks to dissolve where they no longer apply. The Planck units quietly encourage this restraint. They suggest that the universe is not obligated to be intuitive at all scales. As this understanding settles, it becomes clear that Planck energy is not an isolated curiosity. It is part of a family of limits that define the structure of reality itself. These limits do not diminish the universe. They give it coherence. Without them, infinities would run unchecked and stability would be impossible. And so, the birth of Planck units marks a turning point in our understanding. A recognition that nature carries its own measurements, independent of us, measurements that tell us not only how far we can go, but when we must pause and listen instead. As we continue this quiet journey, a new question naturally rises. If these units define where our theories fail, what exactly happens when gravity and quantum mechanics meet there? What kind of reality waits at that intersection? That is the threshold we approach next. Part 4. When gravity joins the quantum world. Gravity is astonishingly weak at everyday scales, yet overwhelming at the smallest ones. As energy is compressed into a tiny region, gravity grows stronger, not weaker. At the Planck scale, gravitational effects become as significant as quantum fluctuations, and neither theory can dominate without contradiction. For most of your life, gravity has felt gentle. It holds you to the Earth without effort. It guides rivers downhill and keeps the moon in its quiet orbit. Compared to other forces in nature, gravity seems almost polite. A small magnet can lift a paperclip against the pull of the entire planet. An electric spark can overpower gravity with ease. For centuries, this weakness made gravity feel simple, almost secondary. Quantum mechanics, by contrast, feels restless and intense. It governs the jitter of particles, the flicker of probabilities, the strange rules that allow things to be both wave and particle at once. At atomic scales, gravity barely enters the conversation. Its influence is so small that quantum equations safely ignore it. This separation has allowed physics to flourish, building precise models for the very large and the very small without forcing them to agree. But this calm division is an illusion created by scale. As you move away from the everyday world and toward smaller and smaller regions of space, energy density increases. Not energy spread out gently, but energy packed tightly, focused into a tiny volume. And gravity, unlike the other forces, responds not just to mass but to energy itself. The more energy you confine, the stronger gravity becomes. This is the quiet turning point. At first, gravity's contribution is negligible. Quantum fluctuations dominate, and spacetime remains a smooth backdrop. But as you push further, compressing energy into smaller regions, gravity begins to rise from the background. Its influence grows steadily, predictably, following Einstein's equations with unwavering patience. By the time you approach the Planck scale, gravity can no longer be treated as a correction or an afterthought. It stands shoulder to shoulder with quantum mechanics. The two frameworks meet directly, and neither is willing to yield. Quantum mechanics insists that uncertainty must increase as you confine particles more tightly. Positions blur, energies fluctuate. The act of confinement itself injects randomness. General relativity, on the other hand, insists that concentrated energy curves spacetime, shaping the odd paths particles can take and even altering the flow of time. One theory thrives on uncertainty, the other demands precise geometry. When these demands collide, contradictions emerge. Imagine trying to describe a region of space so small that quantum fluctuations violently disturb its structure, while gravity simultaneously tries to impose curvature and order. Quantum theory predicts a storm of possibilities. Relativity predicts a smooth but deeply curved geometry. Together, they describe a world that cannot exist as written. This is not a failure of nature, it is a failure of language. Our equations were never designed to operate here. Quantum mechanics assumes spacetime exists as a fixed stage. General relativity assumes spacetime can be treated as a continuous fabric. At the Planck scale, both assumptions break down. The stage itself fluctuates, the fabric frays. Physicists sometimes describe this regime as one where spacetime becomes quantized, though what that truly means remains unclear. Does space come in tiny indivisible units? Does time tick in discrete steps? Or is the reality even stranger, with geometry emerging only statistically, the way temperature emerges from the motion of countless molecules? What we do know is that gravity's weakness is deceptive. Its strength is not fixed. It depends entirely on scale. Spread energy out and gravity whispers. Compress it enough and gravity roars. Black holes are the clearest demonstration of this truth. They form not because gravity suddenly changes its nature, but because enough energy or mass is packed into a small enough region. At their centers, densities approach the Planck regime. Our equations predict singularities, points of infinite curvature, but most physicists now believe these infinities signal a breakdown of theory, not reality itself. In that sense, black holes are not just exotic objects. They are laboratories where gravity and quantum mechanics are forced into conversation. Hawking radiation, for example, arises precisely because quantum effects cannot be ignored near a gravitational horizon. It is one of the few places where we have indirect evidence that the two frameworks must ultimately merge. As you rest here, it's worth appreciating how far removed this tension is from your immediate experience. The gravity holding you in place is gentle because the energy densities around you are low. Spacetime is smooth because fluctuations average out. The universe feels stable because you inhabit a region far from these extremes, yet the same laws apply everywhere. In the earliest moments after the Big Bang, the entire universe existed in a state where gravity and quantum mechanics were inseparable. Energy densities were immense, distances were unimaginably small. Spacetime itself was dynamic and volatile. Whatever rules governed that era shaped everything that followed, from the distribution of galaxies to the flow of time itself. Understanding that era requires understanding how gravity joins the quantum world. It is not a minor technical problem. It is one of the deepest questions in science. Without an answer, our picture of the universe remains incomplete at its foundation. This is why so many theoretical approaches begin here. String theory proposes that particles are not points, but tiny vibrating strings, spreading energy over a finite length and softening gravitational collapse. Loop quantum gravity suggests that spacetime itself has a discrete structure, preventing infinite curvature. Other approaches imagine emergent gravity, where spacetime geometry arises from deeper quantum relationships. None of these ideas has yet been confirmed, but all share a common motivation: to find a description where gravity and quantum mechanics no longer contradict each other at the Planck scale. There is a quiet elegance in this pursuit. It is not driven by spectacle, but by consistency. Physicists are not seeking drama at the smallest scales, they are seeking peace. A theory that remains calm when energy and geometry intertwine, that does not tear itself apart under its own assumptions. Until that theory arrives, the Planck scale remains a place of whispers, not silence, but murmurs, hints, boundaries traced in equations rather than experiments. It tells us that gravity is not merely the force that shapes planets and stars. It is woven into the deepest structure of reality, waiting patiently until conditions force it to speak. As this part of the journey comes to rest, another question gently emerges. If gravity becomes dominant when energy is compressed enough, just how much energy are we talking about? What makes Planck energy so extraordinarily large, and why does the universe choose that scale? That is the next quiet mystery waiting ahead. Part 5. Why Planck energy is unimaginably large. Planck energy is not small, it is immense. Concentrated into a single particle-sized region, it rivals the energy of a speeding freight train compressed into a space smaller than an atom. This is not an energy we expect to measure directly. It exists as a signpost, warning us where known physics can no longer travel safely. At first glance, this feels backwards. We tend to associate small things with small energies. A grain of sand feels gentle. An atom feels delicate. Surely the deepest layers of reality should be quiet and subtle. But physics tells a different story. At the smallest scales, energy does not fade away. It intensifies. To understand why, it helps to return to the simple rule that has guided us all along. To see something smaller, you must use higher energy. This rule does not bend for intuition. It does not soften for comfort. It applies with the same calm insistence whether you are studying cells or quarks. And when you follow it all the way down, it leads somewhere startling. Each step towards smaller distances requires probes with shorter wavelengths. Shorter wavelengths mean higher frequencies. Higher frequencies mean higher energies. This escalation is not linear. It accelerates. By the time you approach the Planck length, the energy required has grown to a scale that dwarfs anything encountered in ordinary physics. Planck energy emerges precisely from this escalation. It is the energy associated with a wavelength equal to the Planck length. And because that length is so extraordinarily small, the corresponding energy must be extraordinarily large. There is no alternative. The mathematics leaves no room for compromise. What makes this energy feel so shocking is not just its size, but its density. It is not spread out gently over space. It is imagined as being concentrated into a region so tiny that the very idea of size begins to lose meaning. Energy packed this tightly becomes something more than energy. It becomes gravity. This is the key to why Planck energy matters. Gravity responds not to how much energy exists, but to how concentrated it is. A star contains far more total energy than any particle experiment, yet its energy is spread over a vast volume. The curvature of spacetime it produces is significant, but manageable. Compress that same energy into a much smaller region, and gravity's response becomes extreme. At the Planck scale, energy density reaches a tipping point. The curvature of spacetime caused by that energy becomes comparable to the quantum fluctuations already present. Geometry itself becomes unstable. The smooth stage assumed by classical physics begins to buckle under the weight of what it carries. This is why Planck energy is often described as a threshold rather than a target. It marks the point where adding more energy does not grant more access, but instead closes doors. Beyond it, our current theories predict gravitational collapse, horizons, and loss of information. The universe stops allowing clean questions. It is important to pause here and notice something subtle. Planck energy is not large in the everyday sense. It does not mean the universe is full of violent explosions at small scales. On the contrary, these energies are almost never realized. The everyday world is calm precisely because energy densities are low. Life exists because Planck scale conditions are rare. Planck energy is large because the Planck length is small. The two are inseparable. One defines the other. This pairing ensures stability. If extreme energy densities were easy to achieve, space-time itself would be fragile. Black holes would form constantly. Structure would be impossible. The universe would be a chaotic place, unable to support long-lived patterns. Instead, the universe places its most dangerous energies behind extraordinary barriers. To reach Planck energy in a tiny region would require conditions far beyond anything we can engineer. Even the most powerful particle accelerators on Earth fall short by many orders of magnitude. And this is not a failure of technology. It is a feature of reality. You can think of Planck energy as a kind of cosmic insurance policy. It ensures that the deepest layers of reality are protected from casual disturbance. Only in the most extreme environments, near black holes or at the very beginning of the universe, do such energies naturally appear. Everywhere else, the universe remains safely below this threshold. There is also something philosophically grounding about this scale. It reminds us that the universe is not obligated to be endlessly penetrable. Curiosity has limits, not because it is unwelcome, but because stability requires boundaries. Without such limits, existence itself might unravel. As you sit quietly, perhaps letting your breathing slow, consider how distant this energy is from your own experience. The chemical energy in your body, the thermal energy in the air, the light energy entering your eyes, all of it is gentle by comparison. These energies interact without distorting space or time. They coexist peacefully, allowing complexity and awareness to arise. Yet beneath that calm surface, the equations remember the Planck scale. They remember that if conditions were different, if energy were compressed enough, gravity would surge and geometry would respond. The calm you feel is contingent. It is the result of living in a universe that rarely approaches its own limits. This perspective also reframes how physicists think about unification. Any theory that claims to describe reality at all scales must account for why Planck energy is so high and why it is so rarely accessed. It must explain how quantum fields behave when gravity becomes unavoidable and why spacetime does not tear itself apart under ordinary conditions. Some theories suggest that energy cannot be localized beyond a certain point, effectively spreading itself out and preventing collapse. Others propose that spacetime has a smallest unit, preventing infinite concentration. Still others imagine that gravity weakens or changes character at extreme scales. Each approach is an attempt to understand why Planck energy is both necessary and unreachable. What unites these efforts is an acceptance of the scale's significance. Planck energy is not arbitrary. It is not a coincidence. It is the natural outcome of combining the fundamental constants of nature. It tells us something deep about how reality is stitched together. There is a quiet humility in this realization. We often imagine progress as pushing further, digging deeper, breaking through barriers. But Planck energy suggests a different model, one where progress sometimes means recognizing boundaries and learning to listen rather than force. As this part of the journey settles, the image of immense energy compressed into vanishingly small space lingers. It is a reminder that the universe's most powerful forces are not always loud or visible. Sometimes they exist only as limits, as silent guardians of coherence. And as we continue forward, another question gently takes shape. If space-time itself begins to break down at these energies, what does it actually look like at that scale? Is it smooth, grainy, turbulent, or something beyond description? That is the quiet mystery waiting in the next part of our exploration. Part 6. The Illusion of Smooth. Space-time. At human scales, space appears continuous and calm. But near the Planck scale, space-time may flicker, foam, and fluctuate. Distance itself becomes uncertain. Time loses its steady rhythm. The smooth fabric Einstein described may dissolve into something grainy and restless beneath. When you look around you, space feels dependable. A room has corners. A road stretches smoothly into the distance. Time passes in steady seconds, each one indistinguishable from the last. These impressions are not illusions in the everyday sense. They are accurate descriptions of reality at the scale where human lives unfold. But physics has learned again and again that what feels continuous is often an average, an emergent calm arising from deeper motion. Einstein's theory of general relativity describes spacetime as a smooth geometric fabric. Mass and energy curve this fabric, and that curvature guides motion. Planets follow gentle arcs. Light bends around stars. Time slows near heavy objects. For more than a century, this picture has passed every experimental test placed before it. At astronomical scales, it is astonishingly precise. Quantum mechanics, however, tells a very different story at small scales. There, nothing sits still. Fields fluctuate even in apparent emptiness. Particles appear and vanish. Uncertainty is not a flaw in measurement, but a fundamental feature of nature. Atoms do not have sharp edges. Positions blur. Energies jitter. As long as these two descriptions operate in separate domains, there is no conflict. Spacetime can be smooth where quantum effects average out, and quantum mechanics can ignore gravity where curvature is negligible. This separation is what allows both theories to work so well, but it is also what hides the deeper truth. As you approach the Planck scale, this separation dissolves. Quantum fluctuations grow more intense as you probe smaller regions. Energy becomes harder to localize. At the same time, the energy involved begins to curve space-time itself. The stage and the actors can no longer be treated independently. The smooth fabric of space-time becomes subject to the same restless uncertainty that governs everything else. Physicists sometimes describe this regime using the phrase quantum foam. It is not a literal foam, but a metaphor meant to capture the idea that space-time may be constantly bubbling with tiny fluctuations. Distances stretch and contract, topologies change momentarily, connections form and vanish, the geometry itself refuses to settle. In such a world, asking for a precise distance may no longer make sense. The ruler you use would be affected by the fluctuations of the space it measures. Time intervals would vary depending on local geometry that never quite holds still. Cause and effect, so clear at larger scales, would blur into overlapping possibilities. This does not mean the universe becomes chaotic everywhere. It means that smoothness is scale-dependent. Just as water looks continuous from afar but reveals molecules up close, space-time may only appear smooth because we observe it from a distance. The calm surface hides deeper motion. There is something deeply soothing in this idea. The stability you experience is not fragile. It is robust precisely because it emerges from countless fluctuations, canceling one another out. The universe does not need perfect stillness to create order. It needs balance. At the Planck scale, that balance shifts. The fluctuations no longer average out. Instead, they dominate. The very notion of a fixed background dissolves. Space is no longer something that exists independently of what happens within it. It becomes an active participant. Some theories suggest that space-time is fundamentally discrete, made of tiny units woven together like a lattice. In this view, smoothness is an illusion created by scale, the way a digital image appears continuous until you zoom in far enough to see pixels. Other theories suggest space-time is not made of parts at all, but emerges from relationships, entanglements between quantum states that give rise to geometry only in aggregate. What these ideas share is a rejection of infinite divisibility. They propose that below a certain scale, asking for smaller distances is like asking for fractions of a thought. The question itself loses meaning. Time, too, becomes uncertain. At everyday scales, time feels like a river flowing steadily forward. But near the Planck scale, that flow may break into discrete events or probabilistic sequences. The idea of a universal now dissolves. Before and after blur into a statistical ordering rather than a strict sequence. This has profound implications for how we think about beginnings. The earliest moments of the universe occurred under Planck scale conditions. Space-time itself was subject to intense fluctuations. Asking what happened before may be like asking what lies north of the North Pole. The language fails, not the reality. As you rest with this thought, notice how gentle your own moment feels by comparison. The floor beneath you does not flicker. The walls do not breathe. Time passes without drama. This is not because the deeper fluctuations have vanished, but because they are averaged away at this scale. The universe is kind enough to be quiet, where complexity needs time to grow. Black holes offer another window into this illusion of smoothness. Near their horizons, space-time is curved but still describable by classical equations. Deeper inside, toward regions where densities approach the Planck scale, those equations predict infinities. Most physicists believe these infinities signal not real points of infinite curvature, but the breakdown of the smooth space-time assumption. In other words, the illusion of smoothness finally fails. Understanding what replaces it is one of the central challenges of modern physics. Does space-time break into grains? Does it fluctuate too violently to define structure at all? Or does a new kind of order emerge, one that looks chaotic from our perspective, but is perfectly consistent at its own scale? There is humility in admitting that we do not yet know. The smooth fabric Einstein described has carried us far. It explains the motion of galaxies and the bending of light with extraordinary grace, but it was never meant to describe everything. It is a chapter, not the entire book. Planck scale physics reminds us that reality has layers. What is true at one scale may be an approximation at another. Smoothness itself may be a statistical property, not a fundamental one. And that realization does not diminish our understanding, it deepens it. As this idea settles, it becomes clear that the illusion of smooth spacetime is not a deception, but a gift. It allows life, memory, and meaning to exist without being overwhelmed by deeper turbulence. It gives the universe room to be complex and calm at the same time. And as we continue this quiet journey, another question gently emerges. If spacetime is not truly smooth at the smallest scales, how does information move through such a restless geometry? Can signals, particles, or even causality survive in a world where space and time themselves fluctuate? That question waits softly ahead, guiding us into the next part of the story. Part 7. Why black holes appear when we look too closely. If enough energy is forced into a tiny region, space-time collapses into a horizon. The closer we try to look, the more likely we are to create a miniature black hole instead. Observation becomes impossible, not due to technology, but because nature itself draws a curtain. At first, this sounds almost poetic, as if the universe were deliberately hiding its secrets. But the truth is quieter and more precise. Black holes do not appear out of mystery or drama. They appear because gravity responds faithfully to energy, no matter how small the region or how brief the moment. When energy is concentrated tightly enough, space-time has only one response left. To understand why this happens, it helps to think again about how we look at things. Seeing, in physics, is never passive. Whether you use light, electrons, or other particles, observation requires interaction. You must send something into a region and watch how it comes back. The finer the detail you want, the more energetic that probe must be. This rule has no exceptions. As you push towards smaller and smaller scales, the energy of your probe increases. At first, the effects are manageable. Particles scatter, fields fluctuate, data returns. But gravity is always there, quietly accumulating the consequences of that energy. It does not care whether the energy is used gently or aggressively. It only cares how much is packed into how little space. At a certain point, the energy required to resolve a region becomes so large that its gravitational effect dominates everything else. The region you are trying to observe begins to curve inward. Light paths bend sharply. Time slows relative to the outside world. And then, without any warning or drama, an event horizon forms. This horizon is not a physical surface, it is a boundary in space-time itself. Beyond it, all paths lead inward. Nothing can return. Not particles, not light, not information. The act of observation has created a region that cannot be observed. This is not a flaw in our instruments. It is a feature of the laws of physics. The idea that black holes can form at extremely small scales may feel counterintuitive because we associate them with collapsed stars and galactic centers. But the underlying principle is the same. A black hole forms whenever mass or energy is compressed within its Schwarzschild radius, the critical size where escape becomes impossible. That radius shrinks as the mass decreases. For very small masses, it becomes unimaginably tiny, but never zero. In theory, if you were to concentrate Planck-scale energy into a Planck-length region, the Schwarzschild radius would be comparable to that size. The result would be a microscopic black hole. It would not last long. Quantum effects would cause it to evaporate almost instantly. But during its brief existence, it would block all information from escaping. This is why physicists say the universe prevents us from seeing beyond certain scales. Not by refusing to answer, but by responding consistently. Push too hard, and gravity intervenes. The curtain falls not out of secrecy, but out of balance. There is something deeply symmetrical about this. The same gravity that shapes stars and galaxies also governs the limits of knowledge at the smallest scales. The laws do not change their character. They simply operate under different conditions. As you sit quietly, perhaps noticing the steady pull of gravity anchoring you in place, it is worth reflecting on how gentle that force feels. And yet, Under the right conditions, it becomes absolute. Gravity does not negotiate. It does not weaken when inconvenient. It waits until the rules demand its full attention. Black holes are often portrayed as violent or destructive, but in this context, they are almost protective. They prevent runaway infinities. They ensure that energy cannot be localized arbitrarily without consequence. They enforce a kind of cosmic modesty, reminding us that not all questions can be forced open. This idea reshapes how physicists think about the limits of measurement. There is no clever workaround, no trick that allows you to sneak a glance beyond the horizon. Any probe energetic enough to resolve finer detail will inevitably contribute to the very collapse that hides it. Observation and obstruction become the same act. This realization has profound implications for the nature of reality. It suggests that there is a smallest meaningful length, not because space is made of bricks, but because gravity forbids deeper inspection. The Planck scale may be less about what exists and more about what can be known. Black holes also introduce a deeper puzzle. What happens to information? If observation becomes impossible beyond a horizon, does information truly vanish? Or is it preserved in some subtle form? This question has driven decades of debate, leading to ideas like Hawking radiation and holographic principles, where information is stored not inside a region, but on its boundary. Even here, the message is consistent. Nature does not destroy information lightly, but it does not promise accessibility either. It may preserve answers in ways that defy intuition, encoded in geometry rather than particles. From a broader perspective, black holes serve as reminders that limits are not failures. They are structural features of the universe. Just as there is a maximum speed, there appears to be a maximum resolution. Both arise from the same underlying harmony between energy, space, and time. It is tempting to imagine that future technology will overcome these barriers, that one day we will peer directly into the Planck scale depths. But the physics suggests otherwise. These limits are not engineering problems, they are conceptual boundaries. To go further, we would need not stronger tools, but new ways of thinking. As this part of the journey settles, notice how calm the universe remains despite these extremes. Black holes do not dominate space. They are rare, isolated, carefully contained. The everyday world is spared from their influence, allowing complexity to flourish. The curtain that gravity draws is not meant to frustrate curiosity. It is meant to preserve coherence. Without it, the universe might collapse into chaos, unable to support structure at any scale. And so, when we look too closely and a horizon appears, it is not a denial. It is a reminder that knowledge has shape, that inquiry has weight, and that sometimes the deepest truths are protected not by secrecy, but by balance. As we move forward in this quiet exploration, another question gently forms. If black holes arise to protect the smallest scales, what role did they play in the earliest moments of the universe, when everything was compressed beyond imagination? That question waits softly in the next part of our story. Part 8. Planck energy and the first moment of the universe. The early universe passed through energies near the Planck scale. In those first instants, space and time were inseparable from energy itself. Whatever laws governed that era left faint echoes, patterns that later shaped expansion, structure, and the arrow of time we still experience. When cosmologists speak about the beginning of the universe, they do so carefully, almost quietly. Not because the moment was small or simple, but because our language strains to describe it. As we trace cosmic history backward, past galaxies, past stars, past atoms, we eventually reach a point where the universe becomes so hot, dense, and energetic that our familiar descriptions no longer hold. This is not speculation. It is the direct consequence of following well-tested equations to their logical edge. At the very earliest moment we can meaningfully describe, energy densities approach the Planck scale. Temperatures soar beyond anything imaginable. Distances shrink to scales where space itself cannot be treated as a passive backdrop. Time, too, loses its independence. It does not tick forward against a static stage. It is bound to the energy and geometry of the universe in a single, inseparable whole. In this regime, the universe is not something that exists within space and time. Space and time are something the universe is still becoming. This is why physicists speak of the Planck epoch rather than the beginning itself. It marks the earliest interval where our equations even begin to make sense. Earlier than this, concepts like before, after, size, and duration lose their footing. The Planck epoch is not the first moment in a familiar sense. It is the first moment our descriptions can reach without contradiction. During this epoch, gravity and quantum mechanics are equally strong. Energy is so concentrated that space-time curvature is extreme, while quantum fluctuations are so violent that no smooth geometry can settle. The universe exists in a state that is neither classical nor quantum as we understand them today. It is something deeper, governed by rules we have not yet uncovered. Yet, even in this uncertainty, the universe does not emerge featureless. Tiny differences in energy density, quantum fluctuations stretched to cosmic scales, become seeds. As the universe expands and cools, these seeds are preserved, amplified, and transformed. What begins as microscopic variation becomes macroscopic structure. This is one of the most remarkable aspects of modern cosmology. The large-scale universe remembers its smallest moments. Patterns imprinted when the universe was smaller than an atom are still visible today in the distribution of galaxies and in the faint afterglow of the Big Bang, the cosmic microwave background. Those faint temperature variations, measured with extraordinary precision by satellites, are not random noise. They are echoes, fossils of a time when Planck-scale physics ruled. They tell us that whatever happened at the very beginning did not wash away entirely. It left a subtle but persistent fingerprint. Planck energy also plays a role in shaping the arrow of time. Today, time flows in one direction. Entropy increases. The universe expands. But this directionality is not built into the fundamental equations of physics, which largely work the same forward and backward. The arrow of time seems to emerge from initial conditions. Those initial conditions were set during the earliest moments when the universe was extremely ordered in certain ways and extremely energetic in others. Planck-scale physics may hold the key to why the universe began in a state that allowed time to unfold the way it does, why there was room for complexity to grow rather than collapse immediately into equilibrium. As the universe expanded from its Planck-scale beginnings, energy densities dropped rapidly. Space stretched, time lengthened, gravity weakened relative to other forces. This cooling allowed the fundamental forces to differentiate, particles to form, and eventually atoms to assemble. Each transition left its own imprint, but all of them trace back to that earliest era. It is important to notice how brief this Planck-scale phase was. It lasted for an unimaginably small fraction of a second, and yet its influence is vast. This is a recurring theme in physics. Short, intense moments can shape everything that follows, provided they occur under the right conditions. Black holes offer a smaller scale analogy. Their intense gravity shapes regions far beyond their immediate size. In the early universe, Planck-scale conditions acted like a cosmic black hole turned inside out, influencing the geometry and evolution of everything that came later. There's a temptation to imagine the beginning as a singular explosion, a point where everything emerged all at once. But modern cosmology paints a subtler picture. The universe did not explode into empty space. Space itself expanded. And that expansion was governed by the energy present at each moment, including those near the Planck scale. What happened before the Planck epoch remains an open question. Some theories suggest a prior phase, a bounce, a contraction, a timeless quantum state. Others suggest that the question itself may be ill-posed. The time as we know it begins only after Planck scale conditions ease. In this sense, Planck energy defines not just a physical boundary, but a conceptual one. It marks the edge of history as we can currently tell it. Beyond that edge, we cannot confidently say what happened, not because nothing happened, but because our words no longer apply. There is something profoundly humbling about this. The universe allows us to reconstruct its story with remarkable detail, billions of years of expansion, star formation, and evolution. And then, at the very beginning, it asks us to stop, to acknowledge the limits of our narrative. As you lie quietly, perhaps letting the idea of cosmic time stretch gently in your mind, consider how small your own moment feels compared to these scales. And yet, it exists because of them. The calm, low-energy universe you inhabit is the outcome of an intensely energetic birth. Planck energy was not a lingering condition. It was a passage, a threshold crossed as the universe cooled and unfolded. Its role was not to dominate forever, but to set the initial geometry, the initial fluctuations, the initial direction. Even now, the expansion of the universe carries faint memory of that beginning. Space continues to stretch. Time continues to flow. The patterns seeded at the smallest scales continue to guide the largest structures. Physicists continue to search for a theory that can describe the Planck epoch without contradiction. Such a theory would not merely explain the beginning. It would unify our understanding of space, time, energy, and gravity into a single coherent framework. It would tell us not just how the universe evolved, but why it could evolve at all. Until then, Planck energy remains a quiet guardian of the beginning, a reminder that the universe emerged from conditions far beyond everyday experience, yet settled into a state gentle enough to host galaxies, life, and thought. And as this part of our journey comes to rest, another question softly arises. If the earliest universe was governed by Planck scale physics, why do our current theories struggle so deeply to describe it? What exactly breaks down in our equations, and what does that tell us about the nature of reality itself? That question waits patiently, guiding us onward. Part 9. Why our theories disagree at the edge. Quantum mechanics demands uncertainty. General relativity demands smooth geometry. At Planck energy, both insist on being correct and neither can fully yield. The equations produce infinities, contradictions, and breakdowns, not because reality fails, but because our frameworks do. For most of modern physics, this disagreement has been easy to ignore. Quantum mechanics governs the microscopic world with extraordinary precision. It predicts the behavior of atoms, electrons, and light to more decimal places than any theory in history. General relativity governs the cosmic stage with equal elegance, describing the motion of planets, the bending of light, and the evolution of the universe itself. Each theory works so well within its domain that it can feel complete. The trouble begins only when we ask them to speak at the same time. Quantum mechanics begins with a simple but unsettling truth. You cannot know everything at once. Position and momentum blur together. Energy fluctuates. Even empty space seethes with activity. This uncertainty is not noise to be eliminated. It is the fundamental texture of reality at small scales. The equations are built around probability, not certainty. General relativity, by contrast, begins with smoothness. Spacetime is treated as a continuous geometric object. Curvature changes gently in response to mass and energy. Paths are well defined. Events occur at specific locations in a fabric that, while flexible, remains mathematically calm. As long as spacetime itself can be treated as stable, quantum mechanics is content to work within it. As long as quantum fluctuations are small, general relativity can ignore them. This separation has allowed physics to advance rapidly without resolving their differences. But at Planck energy, that separation collapses. Here, quantum fluctuations are no longer small. They are violent. Energy jitters wildly from moment to moment. At the same time, that energy is concentrated enough to curve spacetime dramatically. Geometry itself becomes uncertain. The smooth fabric general relativity relies on begins to tear under quantum stress. When physicists try to combine the equations directly, the results become unmanageable. Calculations explode into infinities. Predictions lose meaning. Quantities that should be measurable diverge without bound. These infinities are not subtle. They are loud signals that something has gone wrong. It is tempting to imagine that these breakdowns mean reality itself is contradictory. But physics has learned to be cautious with that conclusion. In the past, infinities have often pointed not to flaws in nature, but to flaws in description. They signal that a theory is being pushed beyond its intended range. A familiar example comes from classical electromagnetism. When early physicists tried to calculate the energy of an electron treated as a point particle, they obtained infinite results. The solution was not to accept infinite energy, but to revise the framework. Quantum theory replaced the classical picture and removed the infinities by changing the underlying assumptions. Something similar appears to be happening here. Quantum mechanics assumes a fixed space-time background. General relativity assumes spacetime can be treated classically without quantum uncertainty. At the Planck scale, both assumptions fail at once. The equations disagree not because one is wrong, but because each is incomplete. This disagreement reveals something profound. Our most successful theories are not universal languages. They are approximations that work beautifully under certain conditions. When those conditions change, the approximations unravel. There is something deeply human about this. We build models that reflect the scales we inhabit. Our intuition, our mathematics, even our metaphors are shaped by a universe that feels smooth and stable. At the Planck scale, those intuitions no longer apply. Physicists have spent decades trying to resolve this conflict. Some approaches attempt to quantize gravity directly, treating space-time itself as subject to quantum rules. Others attempt to smooth out quantum fluctuations by spreading energy over finite structures, like strings or loops. Still others suggest that space-time and gravity are not fundamental at all, but emergent phenomena arising from deeper quantum relationships. What unites these efforts is an acceptance that the disagreement is telling us something important. The edge where theories fail is not an embarrassment, it is a map. Consider how carefully nature seems to enforce this boundary. Every attempt to localize energy too precisely leads to gravitational collapse. Every attempt to ignore quantum fluctuations at extreme densities leads to contradictions. It is as if reality insists on a new description at this scale, one that does not privilege either uncertainty or geometry, but weaves them together. As you sit quietly, perhaps letting these ideas drift without strain, notice how different this is from everyday problem solving. In daily life, disagreement often means error. In physics, disagreement at the deepest levels often means discovery. It marks the edge of understanding, not its failure. The universe has offered us clues before. The incompatibility between Newtonian mechanics and electromagnetism led to relativity. The incompatibility between classical physics and atomic spectra led to quantum mechanics. In each case, the tension between theories forced a deeper synthesis. The tension between quantum mechanics and general relativity may be the next such turning point. Importantly, this disagreement only becomes unavoidable at extreme energies and tiny scales. Everywhere else, the universe behaves politely. Spacetime remains smooth. Quantum fluctuations average out. The theories coexist without conflict. This is why the world feels coherent and reliable. That coherence is not accidental. It suggests that whatever deeper theory exists must reduce to quantum mechanics and general relativity in their respective limits. It must explain not only why they fail together, but why they succeed separately. This is a tall order. It requires a framework that can describe fluctuating geometry without tearing itself apart and uncertainty without losing structure. It requires new mathematics, new intuition, and perhaps new ways of thinking about what a theory even is. Some physicists suspect that the very notion of space-time as a fundamental entity may need to be abandoned. Perhaps space and time emerge from more abstract relationships, the way temperature emerges from molecular motion. In such a view, the disagreement between quantum mechanics and general relativity arises because both are describing emergent behavior from different angles. Others suspect that symmetry principles hidden at low energies become dominant at the Planck scale, enforcing consistency in ways we do not yet see. Still others suggest that information, rather than energy or geometry, may be the most fundamental currency of reality. For now, these ideas remain untested, but the disagreement itself continues to guide research, shaping experiments, simulations, and thought experiments. It reminds physicists where to look and where to be cautious. there is a quiet comfort in knowing that the universe does not simply dissolve into nonsense at its deepest levels. The breakdowns occur in our equations, not in nature. Reality continues to function even if our descriptions stumble. As this part of the journey settles, it becomes clear that Planck energy is not just a physical scale, it is an intellectual crossroads, a place where our most successful ideas meet their limits and ask to be reimagined. And as we move forward, another question gently rises. If our theories break down because of infinities and contradictions, is there a deeper description that avoids them entirely? One where space, time, and energy are not separate concepts at all, but expressions of a single underlying structure. That possibility waits quietly ahead, inviting us onward. Part 10. Is space made of something smaller than itself? Some theories suggest spacetime may be built from discrete units, woven like a lattice beneath perception. Others imagine vibrating strings or looping geometries. Each attempts to describe what exists beneath the Planck scale, yet none have reached experimental confirmation. When you look around, space feels seamless. There are no gaps between places, no visible pixels in the distance. You can move smoothly from one point to another without ever sensing a smallest step. For most of human history, this continuity felt unquestionable. Space simply was, an empty stage extending endlessly in every direction. But physics has a long history of revealing that apparent smoothness often hides deeper structure. Water feels continuous until you watch it freeze into crystals or break into droplets. Solid matter feels rigid until you learn it is mostly empty space, structured by fields and forces. Again and again, what seemed indivisible turned out to be composed of something smaller. So it is natural to ask the same question of space itself. Is space-time truly continuous, or does it have an underlying structure too fine for us to notice? This question becomes unavoidable near the Planck scale. If space-time were infinitely divisible, then distances could shrink without limit. But as we've seen, physics resists that idea. Attempts to probe ever smaller regions run into gravity, horizons, and breakdowns of theory. These obstacles suggest that something fundamental changes, not just in our measurements, but in what space actually is. One possibility is that space-time is discrete. In this view, space is not a smooth fabric, but a network of tiny units connected in specific ways. Distances would not shrink indefinitely. They would come in minimum steps, like the smallest possible stitch in a cosmic weave. Smoothness would be an illusion created by scale, the way a tapestry looks continuous until you examine the threads. Loop quantum gravity explores this idea in a particularly direct way. It suggests that space is made of tiny loops interlinked in a granular structure. Areas and volumes are not continuous quantities, but take on discrete values, much like energy levels in an atom. At large scales, these discrete units blend into the smooth geometry described by Einstein. At the smallest scales, they reveal a fundamentally different picture. In this framework, space-time does not exist as a background. It is built dynamically from relationships between these loops. Geometry becomes quantized. Curvature arises from how loops connect, not from a smooth surface bending in space. The Planck scale marks the size of these fundamental building blocks. Another approach imagines something even more abstract. String theory suggests that the fundamental constituents of reality are not points at all, but tiny vibrating strings. These strings are not embedded in space the way objects are. Instead, their vibrations give rise to particles, forces, and even space-time itself. Geometry becomes a consequence of how strings interact. In this picture, asking whether space is made of smaller pieces is almost the wrong question. Space is not built from strings. Space emerges from them. The familiar dimensions you experience may be the large-scale manifestation of deeper, tightly curled dimensions that remain hidden at low energies. Both of these approaches challenge intuition in different ways. One replaces smoothness with discreteness, the other replaces geometry with vibration, yet both are attempts to answer the same quiet question: what lies beneath the Planck scale, where our usual descriptions fall silent? There are also more radical ideas. Some physicists propose that spacetime is not fundamental at all, but emerges from quantum information. In these models, entanglement, the deep connection between quantum states, gives rise to the notion of distance. Regions of space are close because their underlying quantum states are strongly correlated. Geometry becomes a map of relationships rather than a physical substance. In such a universe, space is not made of things, it is made of connections. This idea has gained traction because it offers a new way to think about gravity. Instead of treating gravity as a force or a curvature, it becomes an emergent effect arising from how information is organized. Changes in entanglement patterns appear as curvature in spacetime. The smooth geometry we observe is a large-scale statistical behavior, not a fundamental one. What all of these theories share is restraint. They do not claim that space beneath the Planck scale is something we can easily picture. They suggest instead that our everyday intuition about space may be as limited as a fish's intuition about air. We experience only what emerges, not what underlies. As you sit quietly, perhaps letting your awareness rest on the feeling of space around you, it is worth noticing how little effort that experience requires. You do not calculate distances. You do not assemble geometry from parts. Space simply appears. That immediacy is part of the illusion. It hides the possibility that space is the result of countless deeper processes working in perfect coordination. And yet, for all their elegance, these theories remain unconfirmed. No experiment has yet probed directly beneath the Planck scale. No observation has definitively revealed discrete space-time units, strings, or informational geometry. The energies required are too high, the distances too small. Nature has placed this layer well beyond easy reach. This does not mean the ideas are wrong. It means they remain provisional. Physics advances by proposing bold explanations and then patiently waiting for evidence. Sometimes that evidence arrives decades later. Sometimes it never arrives at all, and the idea quietly fades. There is humility in this waiting. It is tempting to demand answers, to insist that reality must be understandable on our terms. But the universe does not hurry. It allows us to glimpse patterns, to test consistency, to refine questions. It does not promise closure. The question of whether space is made of something smaller may ultimately be resolved not by direct observation, but by indirect coherence. A successful theory of quantum gravity will not just describe Planck scale structure. It will explain why the universe looks smooth, why gravity behaves as it does, why black holes obey thermodynamic laws, and why information appears preserved. It will fit seamlessly with what we already know, while extending gently beyond it. Until then, spacetime remains both familiar and mysterious. We move through it without effort, even as its deepest nature remains hidden. That contrast is not frustrating, it is grounding. It reminds us that understanding does not require total access. It requires respect for scale. As this part of the journey comes to rest, another question begins to form naturally. If space may be discrete, vibrating, or emergent, how does that affect the way information moves through the universe? Does causality survive beneath the Planck scale, or does it too emerge only at larger distances? That question waits quietly ahead, inviting us onward. Part 11. Why we cannot build a Planck energy experiment. Even the largest accelerators on Earth fall unimaginably short of Planck energies. To reach them would require machines the size of galaxies. The universe, it seems, does not intend this boundary to be crossed easily, or at all. When people imagine the limits of physics, they often picture technology as the missing ingredient. Bigger machines, stronger magnets, more powerful detectors. Throughout history, this intuition has often been correct. Each generation built instruments that surpassed the last, revealing atoms, nuclei, quarks, and entire cosmic epochs that were once invisible. It is natural to assume the same pattern will continue indefinitely. But Planck energy breaks that pattern. The Large Hadron Collider, the most powerful particle accelerator ever constructed, spans 27 kilometers beneath the border of France and Switzerland. It accelerates protons to energies of trillions of electron volts, smashing them together to recreate conditions not seen since the early universe. By any human standard, this is extraordinary. And yet, compared to Planck energy, it is barely a whisper. The gap is not small. It is vast beyond intuition. Planck energy sits many orders of magnitude above what even the most ambitious future accelerators could hope to achieve. Closing that gap is not a matter of incremental progress. It would require a leap so large that it changes the meaning of engineering itself. To understand why, consider how particle accelerators work. They increase energy by pushing particles through electromagnetic fields over long distances. The longer the path, the more energy the particle can gain. This is why accelerators keep growing in size. There is no shortcut. Energy must be added gradually, step by step. Now imagine what it would take to reach Planck energy. Even if you could build perfect superconducting magnets and eliminate all losses, the distance required would be astronomical. Not kilometers, not planetary scales, galactic scales. Machines so large they would dwarf stars, wrapping around entire solar systems just to accelerate a single particle to the required energy. And even that is only part of the problem. As energies rise, particles become harder to control. Magnetic fields must be stronger. Materials must withstand greater stresses. Radiation becomes more intense. At some point, practical constraints become fundamental ones. The machine would interfere with itself. Its own energy would curve space-time. Gravity would no longer be negligible. In other words, the experiment would begin to encounter the very physics it was designed to study. There is something quietly ironic about this. To study Planck-scale physics directly, you would need to create Planck-scale conditions. But creating those conditions would immediately trigger gravitational effects, possibly even microscopic black holes, that erase the information you hope to observe. The act of experimentation defeats itself. This is not how most scientific limits behave. Usually, limits invite ingenuity. Here, they invite restraint. Nature seems to enforce a separation between what can be inferred and what can be forced. The Planck scale may be accessible indirectly through cosmology, black hole thermodynamics, or subtle quantum effects, but it resists direct confrontation. The boundary is not just high, it is guarded. As you rest with this idea, it may feel frustrating at first. Why would the universe allow us to glimpse so much, only to withhold its deepest layer? But there is another way to see it. The same physics that makes Planck energies unreachable also makes the universe stable. If Planck-scale energies were easy to access, space-time itself would be fragile. Tiny fluctuations could collapse regions into black holes. Structure would be constantly threatened. Long-lived systems, atoms, stars, life, might never form. The universe's refusal to grant easy access to its extremes is precisely what allows complexity to exist. In this sense, the inability to build a Planck energy experiment is not a limitation imposed on us. It is a condition that makes us possible. This realization has reshaped how physicists approach the deepest questions. Instead of asking how to build bigger machines, they ask how to listen more carefully. They search for natural laboratories where Planck-scale physics may have left traces. The early universe, the edges of black holes, subtle anomalies in particle behavior, tiny deviations from expected patterns. Cosmology, in particular, has become a window into energies far beyond what any accelerator could reach. The cosmic microwave background preserves information from a time when the universe itself was the experiment, filled everywhere with energies approaching the Planck scale. By studying its patterns, physicists infer properties of physics at energies they cannot recreate. Similarly, black holes act as amplifiers of extreme physics. While we cannot create Planck energy conditions in the lab, the universe does so naturally in these objects. Hawking radiation, entropy, and horizon dynamics offer indirect clues about how quantum mechanics and gravity interact. This shift, from direct experimentation to indirect inference, is not a retreat. It is an adaptation. Physics has always evolved its methods alongside its questions. When direct access becomes impossible, Consistency, coherence, and convergence become the new tools. There is also a philosophical calm in recognizing that not every question is meant to be answered by force. Some are answered by pattern, some by implication, some by recognizing that the boundary itself is the message. Planck energy tells us that the universe has a scale where intervention gives way to observation and observation gives way to inference. It suggests that reality is layered not just in size, but in accessibility. As you breathe, perhaps feeling the steadiness of the moment, notice how distant these extremes feel. The energies shaping your experience are gentle, the forces are balanced, the universe around you is quiet because it is far from its own limits. And yet, those limits still matter. They shape the equations. They define what is possible. They whisper constraints into every theory that reaches too far. Some physicists suspect that the ultimate theory of quantum gravity may never be tested in the traditional experimental sense. Instead, it may be validated by internal consistency, by its ability to reproduce known physics and resolve contradictions without contradiction of its own. It may be judged not by a single dramatic experiment, but by the calm coherence it brings to everything else. This is a different vision of science, slower, more reflective, less about conquest and more about understanding. The universe, it seems, does not challenge us to overpower it. It challenges us to understand our place within it. As this part of the journey settles, a final question gently emerges. If we cannot build experiments to reach Planck energy, how confident can we be in the theories that describe it? What does it mean to know something we may never directly test? That quiet question waits ahead, inviting us to continue. Part 12. The role of Planck energy in unifying physics. Physicists search for a theory that treats gravity and quantum mechanics as one language. Planck energy marks the place where that language must exist. Any successful theory of everything must remain calm and consistent at this scale, where all forces converge. For over a century, physics has spoken in two voices. One describes the vast architecture of the cosmos, curved spacetime orbiting planets, expanding galaxies. The other describes the restless interior of matter, particles flickering into existence, probabilities replacing certainties, energy arriving in discrete packets. Each voice is precise, each is elegant, and yet when spoken together at the deepest scales, they clash. The dream of unification is not new. Physicists have always searched for simplicity beneath complexity, or a single set of principles that explain many phenomena at once. Electricity and magnetism were once separate forces until Maxwell revealed they were expressions of the same underlying field. Space and time were once distinct until Einstein showed they were inseparable. Each unification did not erase complexity, it revealed deeper order. Planck energy represents the next such threshold. It is the scale where gravity and quantum mechanics can no longer remain strangers. At everyday energies, quantum effects dominate small systems and gravity dominates large ones. The overlap is negligible, but as energy increases and distances shrink, the separation collapses. At the Planck scale, every interaction feels every other. Forces that once appeared distinct begin to converge. This convergence is not just mathematical, it is conceptual. At Planck energy, the very categories we rely on, particle, field, spacetime, force, begin to blur. A unifying theory cannot simply stitch together existing equations, it must rethink the foundation on which those equations are built. This is why Planck energy plays such a central role. It is not merely a numerical scale, it is the point where questions change character. Instead of asking how particles move through space, we must ask how space itself arises. Instead of asking how forces act within time, we must ask what time is made of. Any theory that hopes to unify physics must pass through this narrow gate. It must explain why gravity is weak at low energies but unavoidable at high ones. It must explain why quantum uncertainty dominates the small but yields to classical behavior at large scales. And crucially, it must do so without producing infinities or contradictions at the Planck boundary. This requirement is extraordinarily demanding. String theory approaches this challenge by replacing point particles with extended objects. By spreading energy over tiny but finite lengths, it softens gravitational collapse and smooths quantum divergences. In this framework, Planck energy is not a cliff, but a region where new vibrational modes become relevant. Forces unify because they are all manifestations of the same underlying strings. Loop quantum gravity takes a different path. It attempts to quantize spacetime itself, building geometry from discrete units. In this picture, Planck energy corresponds to the scale where spacetime's granular structure becomes visible. Gravity and quantum mechanics unify because gravity is no longer classical, it is quantum at its core. Other approaches suggest that unification may not involve forces at all, but information. In these views, Planck energy marks the scale where spacetime geometry emerges from patterns of entanglement. Gravity becomes an emergent phenomenon, not a fundamental one. Unification occurs because all physical laws reduce to relationships between information. What these approaches share is a deep respect for the Planck scale. None of them treat it as an inconvenience to be bypassed. They treat it as the place where truth must be negotiated. There is something quietly beautiful about this. The universe does not allow us to unify physics anywhere we choose. It tells us where unification must happen and challenges us to build a language subtle enough to survive there. As you rest with this idea, it may help to notice how natural unification feels in everyday experience. You do not perceive gravity and electromagnetism as separate forces guiding your movements. You experience a single, coherent world. That coherence is real, even if the underlying descriptions are divided. The role of physics is to explain that coherence without breaking it. Planck energy reminds us that coherence at the deepest level cannot be forced. It must be earned through consistency. A unified theory cannot work only where it is convenient. It must remain stable where our current theories fail. This is why unification is slow. It is not a race to publish equations. It is a careful process of elimination, refinement, and listening. Theories are tested not just against experiments, but against logic itself. They are asked to remain calm under extreme conditions. There is also humility in acknowledging that unification may not look the way we expect. Past unifications surprised us. They did not simply combine existing ideas, they transformed them. Space became time. Forces became fields. Perhaps the next unification will transform our understanding of reality just as deeply. Planck energy stands at the center of this transformation. It is the scale where old assumptions fail simultaneously, where spacetime cannot be assumed smooth, where particles cannot be assumed point-like, where causality itself may need reinterpretation. And yet, this scale is not distant from us in a philosophical sense. It shapes the stability of everything we experience. Without a consistent description at the Planck scale, the universe would not hold together. Galaxies would not form. Time would not flow reliably. The calm coherence of reality depends on rules that work even at its deepest limits. Physicists often speak of a theory of everything, but this phrase can be misleading. The goal is not to explain every detail of experience. It is to explain why the laws we have work as well as they do and where they come from. Planck energy is the proving ground for that explanation. As this part of the journey gently settles, it becomes clear that unification is not about dominance, quantum mechanics defeating gravity or gravity absorbing quantum rules. It is about reconciliation, about finding a language that allows both to speak without contradiction. And as we move onward, one final question begins to take shape. If Planck energy defines where unification must occur, what happens if the universe itself enforces that unification in ways we cannot yet see? Could the unfinished nature of our theories be a feature, not a flaw, an invitation rather than a failure? That quiet thought waits patiently, guiding us toward the next chapter. Part 13. Is Planck energy a wall or a doorway? Some see Planck energy as a hard limit, the smallest meaningful scale. Others see it as a hint, a doorway to deeper structure waiting to be understood. Whether it is an endpoint or a beginning remains quietly unresolved. There is a gentle tension in this question, one that has followed physics for decades. When we encounter a boundary in our understanding, we instinctively want to classify it. Is it a wall telling us to stop, or is it a doorway asking us to change how we pass through? Planck energy sits precisely at this crossroads, inviting both interpretations without fully committing to either. To see why, it helps to reflect on how physics has treated limits in the past. The speed of light was once thought to be just another large number, something faster engines might eventually exceed. Instead, it turned out to be a fundamental boundary, reshaping our understanding of space and time. Absolute zero temperature is another such limit, not merely difficult to reach, but conceptually defining the ground state of motion itself. These limits are not disappointments, they are organizing principles. They tell us how reality is structured and where our intuitions must adapt. Planck energy may belong to this same family. As a wall, it represents the smallest scale at which our current concepts retain meaning. Beyond it, words like distance, duration, and even energy lose their clarity. Attempts to push past it lead to horizons, infinities, and contradictions. In this view, Planck energy is not a challenge to overcome, but a line to respect. There is something calming about this interpretation. It suggests that reality is not infinitely deep in every direction, that there is a foundational layer beneath which the question, "What is smaller?" simply no longer applies. The universe in this sense would be complete at its base, self-contained, finite in structure, and protected from endless regression. But there is another way to listen to what Planck energy is telling us. As a doorway, it hints that our current descriptions are not final. The breakdowns we encounter at this scale may not signal the end of understanding, but the end of a particular language. Just as classical mechanics gave way to quantum mechanics when pushed too far, our present theories may be giving way to something deeper when confronted with Planck scale conditions. In this view, Planck energy is not a stop sign. It is a signpost pointing toward a new framework, one that does not yet exist in complete form. The contradictions and infinities are not walls, but pressures, places where the old structure can no longer support the weight placed upon it. This perspective has driven much of modern theoretical physics. Each attempt at quantum gravity treats the Planck scale not as forbidden territory, but as fertile ground. The goal is not to see smaller distances directly, but to understand what replaces distance itself. If spacetime emerges from something deeper, whether discrete units, strings, loops, or information, then Planck energy marks the scale where that emergence becomes visible in principle, even if not directly observable. The doorway may not lead to finer resolution, but to a different kind of description altogether. There is a subtle but important distinction here. A doorway does not promise access in the usual sense. It promises transformation. To pass through it, you may need to leave familiar concepts behind. As you sit quietly with this idea, notice how often such transformations occur in everyday understanding. You do not experience temperature as the motion of molecules, yet that is what it is. You do not feel solidity as electromagnetic repulsion between atoms, yet that is its foundation. Deeper explanations do not replace experience, they reframe it. Planck energy may be asking for a similar reframing. The wall interpretation emphasizes humility. It reminds us that not every layer of reality is meant to be dissected, that some limits preserve coherence by preventing infinite curiosity from tearing the structure apart. In this sense, Planck energy protects the universe from pathological extremes. The doorway interpretation emphasizes hope. It suggests that our current confusion is temporary, that a deeper order exists beyond the noise of breakdowns, that the universe is not hiding its foundation, but waiting for us to learn how to ask the right questions. What makes Planck energy so intriguing is that it supports both interpretations simultaneously. It resists direct probing while inviting theoretical exploration. It blocks experiments while inspiring mathematics. It closes one kind of access while opening another. This duality may not be accidental. The universe often reveals itself through balance rather than absolutes. Light behaves as both wave and particle. Time flows forward locally while remaining symmetric in equations. Perhaps Planck energy is both wall and doorway, depending on how you approach it. As a wall, it tells us that measurement has limits. As a doorway, it tells us that meaning does not. There is also a psychological comfort in accepting that some questions remain unresolved. Modern culture often equates knowledge with completion, as if every mystery must eventually be solved. Physics offers a gentler view. Understanding can deepen even when answers remain open-ended. Clarity does not always mean closure. Planck energy, unresolved as it is, has already clarified much. It has shown us where our theories are strongest and where they falter. It has unified disparate questions under a single scale. It has guided decades of research without being directly observed. In that sense, it is already a doorway, not to a final answer, but to better questions. Consider how different physics would look without this scale. We would not know where to focus efforts. We would not know which infinities matter and which are artifacts. The Planck scale organizes our ignorance, turning it into a structured problem rather than a shapeless mystery. As you breathe, perhaps letting the idea of boundaries soften, notice how this mirrors the rhythm of rest itself. Sleep does not come from forcing the mind to work harder. It comes from allowing effort to give way to trust. Planck energy asks something similar of physics, not more force, but more patience. The universe may not be unfinished in the way a puzzle is unfinished. It may be unfinished in the way a story is unfinished, open-ended, rich with implication, inviting participation rather than resolution. Whether Planck energy is ultimately a wall or a doorway may depend less on the universe and more on us, on whether we insist on carrying old tools into new terrain, or whether we are willing to set them down and learn a new way of seeing. For now, the question remains quietly open. The equations do not yet settle. The experiments do not yet speak. And in that silence, there is space, not emptiness, but possibility. As this part of our journey gently fades, another thought begins to form. If Planck energy remains unresolved, if it resists both conquest and dismissal, what role does that unfinishedness play in science itself? Could uncertainty be not a weakness, but a vital feature of understanding? That question waits softly ahead, guiding us toward the next chapter. Part 14. Why unfinished theories still matter. Even incomplete theories guide discovery. They tell us where questions sharpen, where assumptions break, and where humility becomes necessary. Planck energy reminds science that knowing where we fail is as important as knowing where we succeed. In science, there's a quiet misconception that progress only comes from finished ideas, that a theory must be complete, proven, and polished before it has value. But history tells a gentler story. Some of the most important advances emerged not from answers, but from clearly defined failures, places where equations stopped working, places where predictions dissolved into contradictions, places where understanding paused, not in defeat, but in honesty. Planck energy sits precisely in one of those places. Our current theories, quantum mechanics and general relativity, are not wrong. They are extraordinarily successful. They describe nearly everything we can observe with astonishing accuracy. Yet, when pushed toward the Planck scale, they no longer cooperate. Instead of clarity, they produce infinities. Instead of agreement, they offer tension. This is not a flaw to be hidden. It is a signal to be listened to. Unfinished theories act like signposts. They mark the edges of reliable knowledge. They tell us where assumptions no longer hold, where language must evolve, where intuition must be retrained. Without these edges, science would drift aimlessly, mistaking comfort for truth. Planck energy sharpens those edges. It tells physicists very precisely where familiar tools must be set down. It defines a scale where space cannot be assumed smooth, where time cannot be assumed continuous, where energy cannot be treated as a passive quantity. In doing so, it focuses effort, it narrows the search, it gives direction to curiosity. There is something deeply human in this process. We learn best not when everything works, but when something doesn't. When a familiar explanation fails, it invites reflection. It forces us to ask not just what we know, but why we know it. Unfinished theories create space for that reflection. Consider how many breakthroughs emerged from apparent failure. Classical physics could not explain blackbody radiation, leading to quantum theory. Newtonian gravity could not explain certain orbital anomalies, leading to general relativity. In each case, the incomplete theory did not vanish. It remained valid within its domain, while pointing towards something deeper. Planck energy plays this same role today. It does not invalidate what we know. It contextualizes it. It reminds us that every theory is an approximation, accurate within limits, provisional beyond them. This does not weaken science. It strengthens it. It keeps knowledge flexible rather than brittle. As you rest with this idea, it may feel surprisingly calming. The universe does not demand perfection from understanding. It allows partial truths. It allows layered explanations. It allows progress without finality. Unfinished theories also cultivate humility. They remind scientists that nature is not obligated to align with human intuition or mathematical elegance. Reality does not rush to be understood. It reveals itself slowly, often reluctantly, through patterns rather than proclamations. Planck energy humbles by scale. It places a boundary so far removed from everyday experience that it resists imagination. It shows that even our best frameworks are shaped by the environments in which they were developed. They work where energy is low, space is smooth, and time is stable. At the extremes, new rules may apply. This humility is not resignation, it is discipline. Science advances not by pretending to know more than it does, but by clearly stating where knowledge ends. An unfinished theory is not a broken one, it is a living one, actively shaping the next questions. There is also a quiet trust embedded in unfinishedness. Physicists trust that consistency exists even where they cannot yet describe it. They trust that contradictions point to deeper order rather than chaos. They trust that nature is coherent even when our descriptions are not. This trust is what allows research to continue in the absence of direct experimental access. No one has observed Planck-scale physics directly, and yet its influence is everywhere in cosmology, black hole thermodynamics, quantum information theory. The unfinished theory shapes entire fields, guiding what to measure, what to calculate, what to question. Even outside physics, this idea resonates. Human understanding itself is unfinished. We live comfortably with partial knowledge, building meaning without complete certainty. We make decisions without knowing every outcome. We rest without resolving every question. The universe seems to operate in much the same way. Planck energy, in this sense, reflects a broader truth. Completion is not required for coherence. Understanding does not need to be total to be real. There is also beauty in the fact that unfinished theories remain open to surprise. A complete theory leaves little room for wonder. An incomplete one invites creativity, collaboration, and patience. It allows multiple approaches to coexist, testing ideas not just against data, but against each other. This openness has defined modern physics. Different approaches to quantum gravity exist not because physicists cannot agree, but because the problem is rich enough to support many perspectives. Each approach illuminates a different aspect of the same boundary. Planck energy acts as a shared reference point among them. No matter the method, the question returns to the same scale. That convergence itself is meaningful. It suggests that the boundary is real, even if its interpretation remains unsettled. As you breathe slowly, perhaps letting the weight of these ideas soften, notice how unfinishedness does not feel threatening here. It feels spacious. It leaves room for curiosity without urgency, for thought without pressure. The universe does not demand that we finish understanding it tonight, or ever. It seems content to be explored gradually, patiently, with respect for its depth. In that light, Planck energy is not a failure of science. It is one of its greatest successes. It marks the place where honesty replaces overconfidence, where clarity replaces assumption, where humility becomes a tool rather than an obstacle. And as this quiet chapter settles, one final thought begins to emerge. If unfinished theories still matter, if boundaries guide understanding rather than end it, then perhaps the story of Planck energy is not about limits at all, but about how knowledge grows when it learns to stop pushing and start listening. The thought carries us gently toward the final part of our journey, where perspective widens and the universe settles back into calm. Part 15. Living in a universe with boundaries. Though Planck energy lies far beyond experience, it shapes everything indirectly. It defines stability, prevents infinite collapse, and sets the stage on which galaxies, stars, and time itself can exist. The universe is vast, but not without limits. When you look up at the night sky, it feels endless. Stars scatter across darkness with no visible edge. Space seems to stretch on forever, indifferent to measurement, and yet, beneath that feeling of infinity, the universe is carefully structured. It is held together by boundaries, quiet constraints that do not confine but enable. Planck energy is one of those boundaries. It does not announce itself in daily life. You do not feel it in the weight of your body or the warmth of the air, and yet without it, none of these experiences would be possible. The universe you inhabit depends on limits it rarely approaches. Boundaries in physics are often misunderstood as restrictions, but more often they are conditions of stability. The speed of light limits how fast information can travel, but it also ensures causality. The second law of thermodynamics limits the flow of entropy, but it also defines the arrow of time. Planck energy limits how small and intense interactions can become, but it also prevents the universe from collapsing into chaos. Without such a boundary, energy could concentrate without restraint. Spacetime could fold infinitely. Tiny fluctuations could trigger runaway collapse. Structures would tear themselves apart before they ever formed. The calm universe you experience is possible because extreme conditions are rare, contained, and regulated by scale. In this sense, Planck energy acts like a quiet guardian. It enforces balance without intervention. It ensures that while gravity can be strong, it cannot dominate everywhere at once. That while quantum uncertainty exists, it does not dissolve reality into noise at human scales. As the universe expanded from its energetic beginning, it crossed this boundary and never looked back. Energy densities dropped, space-time smoothed, forces differentiated, complexity became possible. The Planck scale receded into the background, no longer active, but never irrelevant. It remains embedded in the equations, shaping what is allowed and what is forbidden. Stars form because gravity can gather matter without triggering collapse at every scale. Atoms exist because quantum mechanics stabilizes electrons without letting them spiral inward endlessly. Galaxies persist because space-time remains smooth over vast distances. Each of these balances traces back, indirectly, to limits defined at the deepest level. Living in a universe with boundaries also shapes how we understand ourselves. We are creatures of the middle scale, too small to experience cosmic expansion directly, too large to sense quantum fluctuations. We exist in a narrow window, where forces balance gently enough to allow memory, thought, and rest. This is not an accident. It is a consequence. If Planck scale physics behaved differently, the window might not exist at all. There would be no stable atoms, no long-lived stars, no slow passage of time. The universe would be either frozen or violently unstable. The fact that you can lie still, listening, is evidence of a cosmos that respects its own limits. There is also something emotionally grounding about this realization. We often imagine meaning arising from boundlessness, from infinite space, infinite possibility. But here, meaning arises from constraint, from a universe that knows when to stop, when to soften, when to allow things to last. Planck energy reminds us that not everything needs to be accessible to be influential. Some of the most important structures are invisible, not because they are hidden, but because they operate quietly in the background. In daily life, boundaries serve a similar role. Sleep requires limits on stimulation. Calm requires limits on motion. Stability requires limits on change. The universe mirrors this pattern at every scale, from biology to cosmology. This perspective also reframes our relationship with knowledge. We do not need to pierce every boundary to understand the whole. We need to recognize which boundaries define coherence and which invite exploration. Planck energy does both. It marks an edge while shaping the interior. As you breathe, perhaps noticing the rhythm of inhalation and exhalation, you may sense how natural boundaries feel. They create cycles. They create rest. They create continuity. A universe without boundaries would be exhausting, endlessly unstable, incapable of sustaining anything long enough to be known. The vastness of the cosmos is not diminished by its limits. It is made possible by them. Planck energy also offers a quiet reassurance. Even at the deepest level, reality is not arbitrary. It is structured. It has scales. It has thresholds. These features are not imposed from outside. They arise from the interplay of the universe's most fundamental principles. You are living in a universe that holds itself together, and that, perhaps, is the most comforting insight of all. The cosmos does not teeter on the edge of collapse. It does not unravel when unobserved. It rests within its own constraints, unfolding gently over billions of years. As this final chapter settles, the questions that once felt sharp begin to soften. The unfinished theories, the unreachable energies, the unseen structures, they are not sources of anxiety. They are signs of depth. The universe does not rush toward completion. It unfolds. And you, in this quiet moment, are part of that unfolding. Supported by boundaries you will never touch, shaped by scales you will never reach, yet perfectly at home within the calm region they make possible. As the story comes to rest, there is nothing left to solve, only space to breathe, to feel the steadiness of a universe that knows its limits, and in knowing them, allows everything else to exist. As this quiet journey comes to a close, the universe settles back into stillness. We've traveled to the smallest edges of meaning, where energy becomes gravity, where space and time lose their familiar shapes, and where our best theories learn to pause rather than push. We did not arrive at a final answer, only at a deeper calm. Planck energy remains unfinished, not as a flaw, but as a reminder that the universe is not obligated to be fully revealed, only faithfully experienced, that boundaries are not failures of understanding, but the structures that allow understanding to exist at all. You live far from these extremes, in a gentle region where forces balance, where time flows steadily, and where space feels smooth beneath thought and breath. That calm is not accidental. It is made possible by limits written deep into reality, limits that hold the cosmos together even when unseen. As you rest now, you don't need to solve anything. The universe does not ask that of you. It only asks that you exist within it, quietly supported by laws older than stars, softer than silence. If this slow exploration brought you peace, I'm truly grateful you shared this moment with me. Thank you for being here, for listening, and for allowing curiosity to soften into rest. Now there's nothing left to follow, nothing left to reach, only the steady rhythm of the universe carrying you gently onward.